So I'm with SSC Pacific, as we're called now. Through various name changes and reorganizations, this organization has been in San Diego for about 75 years. I'm a native San Diegan. I haven't been there quite that long. Also have facilities in Hawaii, Guam, Japan, Philadelphia. We are a DoD civilian organization, around 4,000 employees. Our role is kind of the systems that overarch platforms, not ships, not subs, the things that kind of connect everything else. Information dominance is the key word there too. Within SSC Pacific, this is kind of an overview slide of what's going on in what we call the Unmanned Maritime Vehicle Lab. Variety of unmanned systems. There's a separate group that works on unmanned ground systems, but a lot of our work is with UUVs. You know, there's kind of names of projects and some sense of who the sponsors are for some of this work. Getting in the last few years a little bit into unmanned surface vehicles. You see the catamaran there and another catamaran here. And then the UAV is actually capable of, or will be capable this year of, landing on the unmanned surface vehicle. So launching both air vehicles and UUVs from a surface vehicle. Cooperative autonomy, tying those things together. A bit of effort with gliders as well. So one of the bubbles there on the previous slide, WBIED, waterborne improvised explosive devices. That's an effort that we were working on primarily, started about 2.5, 3 years ago. So it was a three-pronged effort. This is funded by JIDO, Joint IED Defeat Organization. After several years of great successes in the land domain, they needed to take a look at what was going on in the underwater domain, waterborne IEDs. So three-phase approach. A detection sensor, kind of a wide area, look out, you know, a kilometer kind of a radius, incoming threats. Number two, assessment. Go out there and take a look at something if it's detected by the detection sensor, provided that queuing information of where do you go look. Number three, if something gets through your first two security curtains, how do you do remediation? Looking at the ship's hull, looking at complex areas on the quay wall, pier, etc. like that. So John Wood's presentation yesterday, if you were in the room, really focused on this one. So I'm going to focus on this one, swimmer threat identification. So the idea with this piece of the WBIED effort, swimmer threat identification, number one, you get the cueing from the long-range sensor, tells the surface vehicle where to go. Surface vehicle jets out there, 5 to 8 knots kind of speed. At that point, all the underwater sensors, the ROV is retracted, everything's above water. It's swift, it's smooth. Gets on station and yeah, this doesn't show it great. But the arm goes down, the sonar's in the water, you're able to start taking a look. We call that mode 2. Mode 3, you actually detach the ROV, free swimming, get to where you need to be to optimize that sonar imagery, maybe above, slightly above, but anyway, you can go down to mid-column, possibly approaching the bottom, optimizing that imagery, taking a look at what you're up against. You know, the question you're trying to answer, is this a false alarm? Is this a marine mammal? Is it actually a diver? If it's a diver, how many divers? How are they equipped? Those kind of questions to inform the response. When it's in that following mode, or when the ROV is being piloted, then the surface vessel is in an automatic follow mode and managing its own tether. Okay, so this isn't an effort that we stepped into ourselves. It kind of stands on the shoulders of various others. The first was an effort called RILS, sponsored by Office of Naval Research, executed by Necton. Necton was eventually purchased by iRobot. Their Maritime Systems Division, they shut down what they had in North Carolina, moved it up to Bedford, Massachusetts. They are now out of the maritime industry, and that's kind of how we got more directly involved. Meanwhile, two of the co-authors here, myself and Dr. Jopik, worked, as was stated in the introduction, at CMRE, the facility in La Spezia, Italy, NATO work. We were doing related work with surface vessels, both for port protection and for mine countermeasures, using some of the same technologies, including, for example, the BlueView sonar and imaging with that. So when iRobot got out of the maritime business, the responsibility for the project fell directly to us. We executed STID and showed that at a demonstration, 32nd Street down the way in San Diego Bay last September. Through the next fiscal year, we updated that, kept almost the same name, but now it's Submerged Threat Identification and Neutralization. So I'll get into more of that and how we kind of adapted what we had for another mission. Along the way on both of these, a lot of help from Seabite. What they provided primarily was the operator control unit, the GUI, and that's based closely on something that's used within the EOD community broadly. Okay, so from the beginning, we were looking at both monohull and multi-hull designs. These drawings are from when iRobot was still handling the project, but doing some of the trade-offs there. Speed, stability, weight, all that. They opted for the monohull. We'll get to that in a minute. The other key piece is what are we going to do the imaging with? And I believe right from the start, Greg was involved in this with the dual frequency sonar. So it's a horizontal sonar with a 135-degree beam at 450 kilohertz, vertical sonar at 45-degree beam operating at 900 kilohertz. So both in the same package, providing all of that. And that's kind of the meat of what I'll get to towards the end of this presentation, is the imagery from those. So this is again still with the iRobot design and kind of the level of completion that they were able to bring the project to. So you see the monohull primary platform. It has most of the payload on it. Can't really tell what's going on there. But they demonstrated successfully the mode 1 operation. You know, the ability to zip out there at 5, 6, 8 knots, given that targeting information. So this looks a little bit different in a CAD drawing, but there were some stability problems with the monohull platform, not real surprisingly. This platform is bigger than we need, but it was really a platform of availability. That availability came from CMRE. When the two of us departed CMRE, we were obviously on good terms with what was going on at NATO, and that's the idea of the NATO facility, is develop things that might be of use to the member countries within NATO. So first it became a discussion of the software that was developed there for vehicle autonomy. And then it became a discussion of, hey, I don't think you're using these hulls anymore. Is that right? Can we kind of borrow the hulls and put them to use in a project? So those hulls are on loan right now to SSC Pacific, and we're using them. So that's CAD drawing, and that's what it really looks like when we kind of did our first tests in our test pool transdeck up there on Point Loma. And you see really the package in the middle there is really what we received on the contract from iRobot as an incomplete platform, and put that on the catamaran. Testing in the bay, it's kind of a view of what's going on with, you have the deployment arm, in this case the ROV and the sonar out of the water, doing its high-speed part of the operation. Another helping hand from CMRE was with the float. So you see the first diagram where there were PVC floats added to compensate for the weight of the payload being carried around. Happened to have another custom float that had been milled out from CMRE that provided the right amount of flotation, and put that to use. Okay, so as I said, kind of the way the discussion started in what can we share, what can we transition from the NATO facility, was the software and autonomy. So first let me back up and point out that the problem isn't easy. You got a moving vehicle and a moving target in a swimmer. Getting those together and trying to put that in the frame and get a good sonar image is not a trivial task. It's complicated further in our system because you have the ROV separated from the surface vehicle, potentially. So there's a level of autonomy necessary in order to make this feasible for a single operator. In any case, you're doing lots of good things that unmanned systems are supposed to do. You're keeping the operator away from danger, operating over that remote link, avoiding the dull, dirty, and dangerous. But there's a level of autonomy necessary, even with the piloting of the ROV, to make it manageable by one operator, nominally. Okay, so the autonomy backbone we have used. It's called Moose, was initially developed at Oxford University, expanded greatly at MIT, done some collaboration with MIT over the years in a number of related efforts. What it is a set of open source C++ modules, but there's a level of familiarity with working with it that it's not just like you speak C++, it's kind of like you speak Moose, and there's a lot you can build on there. There's building blocks that you can quickly put into operation. So it happens that iRobot was using this framework. 2 of the 3 of us were familiar with it. It was a quick transition for those reasons. So again, reviewing kind of the typical mission sequence, transit out quickly to the target location, transition to mode 2, sonar and ROV in the water, follow if the target's moving. Mode 3, ROV detaches, is taking a closer look, and then the surface vessel is following. Examples of the behaviors executed. This is all part of the Moose IVP framework, but these are some particular things. This is from a presentation a few years ago that was made at a conference at MIT by some of our NATO colleagues. So following at a certain distance or making a circle. This doesn't really apply because we don't have a side-looking sensor with a field of view to the side. Things we were working from. Okay, something of an overview of the operator control unit. Horizontal and vertical images from the BlueView. See the vertical images turned vertical, so this way is actually up. In the middle, you would normally have a larger or a more useful map. In this case, we have shown something with the depth. So there's the surface, there's the bottom, and the vehicle is practically sitting on the bottom. And then you have video both from the surface vessel and from the ROV. So that's kind of what the operator has to work with and what they're looking at. And again, this is C-Byte, and it's based closely on their coin product. It's widely used within EOD community. So this is operations down at 32nd Street, where we did a number of trials going after divers. See the catamaran out there, and dive boat perhaps in the midst of retrieving divers. Here's kind of a reconstruction GPS tracks from an actual run. So again, the 3 modes. Been over this a few times. High-speed transit out, arm goes down. It's moving slower, it's got the sonar in the water, gets on top of the divers, follows the divers for a while. Divers are recalled. At that point, the vehicle just kind of drifts off, and we go to all neutral, and then drive it back and be ready to start again. This is kind of typical of image with open circuit divers in that mode, where you're not actually detaching the ROV, you're on the surface. What you're following is 2 bubble trails, a pair of divers. You can kind of see their different breath rates, and what you're seeing is kind of a cloud of bubbles each time they exhale. And this is at a scale of 24 meters. So the idea at this point was just to get them in view at 24 meters, not to get rock solid imagery. But I mean, that's characteristic of diver. If it's open circuit, that's what you're going to see. Also have some examples of that they aren't blowing bubbles, so we'll get to those also. There's a level of automatic target recognition. This was again done by C-Byte, also done by C-Byte. Kind of latches on to a bright spot that's about the right size, marks that for you, and we have the ability, although we haven't done much with it, to feed that back into the autonomy. So in much better than average water clarity conditions, this is what it might look like with the ROV detached, chasing a diver. Can't tell how great that is with this light, but that's exceptional water quality. That's San Clemente Island off of about 70 miles offshore. And that's a BlueView image from that kind of situation. Bubble trail, diver. Okay, if you were in the room yesterday, you're going to think you recognize the first video I'm going to show. But hang with it. The first minute is the same, but then it takes a different branch. So I have about a 5-minute video that I'm going to let the narration take over, and then I've got some BlueView samples that I'll get into.
whether securing ports and harbors during conflicts or aiding humanitarian relief efforts, U.S. Navy worldwide operations often require visiting areas where the threat of swimmer or diver-placed explosives is very real. In response, the United States Central Command issued a Joint Urgent Operational Need Request to counter waterborne improvised explosive devices, or WVIEDs. The Chief of Naval Operations Expeditionary Warfare Division, OPNAV N957, working with the Joint Improvised Explosive Device Defeat Organization, JIDO, sponsored 3 initiatives at Space and Naval Warfare Systems Center Pacific, each dealing with a specific portion of this waterborne threat: detection, assessment, and response, with response including localization, identification, and neutralization. The first of the 3 initiatives is mobile queuing with in-volume and bottom search to detect suspicious contacts in the water column at extended ranges, whether they were a swimmer or diver, before they reach a security perimeter. The second is swimmer threat identification, which security personnel can use to make positive identification of the swimmer or diver attempting to enter a security perimeter. And the third is a sensor-based stabilized ROV for WVIED identification and neutralization. Building on the JIDO STID effort, which developed a USV and ROV combination that could identify and track swimmer or diver targets in the water column, PMS EOD funded SSC Pacific to add a mine neutralization capability to the system. Government development of this system was greatly accelerated by virtue of software and hardware transitioned from CMRE, a native facility in Italy. In its original configuration, the ROV was equipped with a camera and a dual-frequency BlueView sonar, providing both vertical and horizontal views of a contact. The new capability of submerged threat identification neutralization, STID-N, was created by adding a COTS video ray gripper to the bottom of the ROV. With this gripper and with the help of video ray, a deployment system was developed, which allows the ROV to deliver a payload to a target. The ROV carries a negatively buoyant payload to the target location and jettisons a flotation package at the same time as the neutralization payload. This maintains the neutral buoyancy of the system in all phases of the mission. With this new capability, the STID-N system can rapidly and autonomously transit to a search area in Mode 1, where the ROV is out of the water. Upon arriving at the search area, STID-N transitions to Mode 2 by autonomously lowering its arm holding the ROV. This places the sonar in the water and autonomous searching can begin. If an item of interest is found, the ROV can be undocked from the arm for a closer inspection, which is Mode 3. In Mode 3, while the operator manually drives the ROV with a joystick, the USV system autonomously maintains the desired distance from the ROV and performs
Okay, just watch this first one. And then I asked the question, what just happened? So we'll get into breaking down imagery and seeing what it should look like, what happened. So what should divers look like? So this is German divers with closed circuit gear, no bubbles. So they come in low. You've actually got a shadow projected on the bottom. Pretty nice imagery. So in contrast to kind of the bubble trail we saw otherwise, that's maybe what you're looking for with a closed circuit diver. So here's an image from horizontal sonar in our test pool. Not real distinct at first. See a diver swimming by. So here's a view of what was actually happening. There's the ROV. There's the diver. You can see the diver has very little target. Not even a wetsuit, no tanks, nothing. Pretty minimal. And this is how the vertical sonar can also help you out in this distinguishing. In these cases, I haven't rotated the vertical sonar, so this way is up. What you're seeing, those two lines, this is the bottom, and that's a kind of large box that's down there on the bottom. I paused that there for a couple seconds with a particularly good still image, but having the frame rate on the BlueView is very important in distinguishing. If you had to distinguish it from one or two stills, it's a lot harder to do, but your eye integration, working with this video-like image coming off the sonar, makes it pretty easy to tell what's going on. You can see the legs kicking, everything. So that was another run on the horizontal sonar going out. Notice that it just kind of got diffuse at the end. What happened? Look at the video, same run. Swam out, and then essentially came out of the beam of the horizontal sonar. So that beam's about 20 degrees, and it's pointed down about 6 degrees. So now we're looking at the vertical, where you can see the whole picture. See that the diver swam out and then headed to the surface. Scale, if you can't read it, we're looking at about 10 meters total here. So here's an example of a run just on the vertical sonar. And you can see that with this kind of quick vertical transit, it really wouldn't be in the horizontal beam very long at all. Another horizontal sonar image. Okay, so the question on the audience participation bit here is, did you catch what happened? There's the first frame, there's the last frame. There's the first frame, there's the last frame. Here's the video showing what happened. So that's a metal package with some airspace. And this is actually the first image we showed with the vertical sonar. The other odd thing happening here is a mirror effect. So here's the bottom. The ROV is essentially sitting on the bottom, and you get a mirror image on the other half. Next thing that happens was it went away. Okay, just a couple more bits in this video. Okay, so now we're looking at when the sonar and the ROV are attached on the surface. This is kind of in a search mode lawnmower pattern. This is from a different exercise. The idea at this point is just to kind of pick up bright spots, things that you might want to detach and take a closer look at. So it made a 180-degree turn to port, and you picked up a quay wall there on the extreme right part of the screen. In this case, it was going in for a closer inspection. This is the ROV detached, looking at two bright objects. And actually comes so close that they're within the blanking distance. And I'm going to show the video of that, and then I'll cut it short here. There's the two bright objects, cinder block to the right, and that simulated mine shape to the left. ROV pilot kind of takes a look at both of them, and then goes in for a close look on video with the more interesting of the two. Again, unusual water quality. So my last example back in the PowerPoint presentation will show more of where you need the sonar to get close. start from here. Okay, so again, with the autonomy package we were using, we were easily able to add new capabilities to the system, such as the lawnmower search, when it was originally intended for divers. As I said, when you're in the search mode, you're really just looking for a bright spot. Is it something interesting you want to go take a closer look at? And then you detach the ROV and you get a nice image like that and say, yeah, that's really something I want to take a look at. That's at a distance of about 10 meters. But our water clarity was such that you had to be literally within about 1.5 meters to see anything. Get within 1.5 meters, and you can see it with the video. And then this is another case where we dropped the package, as you saw in the narrated video. So summary, you got, again, the quick, stable platform to get out there, take a good close look with the ROV. The surface vessel, in that case, is doing its automatic following, recover the thing, and go back and do it again.